Basic morphological algorithms: boundary extraction, region filling, extraction of connected components, convex hull, thinning, thickening, skeletons. Boundary extraction. First erode A by B, then make set difference between A and the erosion. The thickness of the contour depends on the size of constructing object B. Region filling. This algorithm is based on a set of dilations, complementation, and intersections. P is a point inside the boundary with the value of 1. xk equals xk minus 1 XOR B in conjunction with the complemented A. The process stops when xk equals xk minus 1. The result that is given by union of A and xk is a set that contains the fill set and the boundary. Extraction of connected components. This algorithm extracts a component by selecting a point on a binary object A. Works similar to region filling, but this time we use in the conjunction the object A instead of its complement. This can be seen in the expression on screen. Convex hull. A is said to be convex if a straight line segment joining any 2 points in A lies entirely within A. The convex hull H of set S is the smallest convex set containing S. Convex deficiency is a set difference H minus S. Useful for object description. This algorithm iteratively applies the hit or miss transform to A with the first of B element, unions it with A, and repeats it with the second element of B, as seen on screen. Thinning. The thinning of a set A by a structuring element B can be defined by terms of the hit or miss transform, as shown. A more useful expression for thinning A symmetrically is based on the sequence of structuring elements, as shown, where Bi is a rotated version of Bi minus 1. Using this concept, we define thinning by a sequence of structuring elements as shown. The process is to thin by 1 pass with B1, then thin the result with 1 pass with B2, and so on, until A is thinned with 1 pass with Bn. The entire process is repeated until no further changes occur. Each pass is performed using the equation as shown. The example for thinning can be diagrammatically represented as shown. Thickening. Thickening is a morphological dual of thinning. Definition of thickening is given by the equation. As in thinning, thickening can be defined as a sequence of operations. The structuring elements used for thickening have the same form as in thinning, but with all the ones and zeros interchanged. A separate algorithm for thickening is often used in practice. The usual procedure is to thin the background of the set in question and then complement the result. In other words, to thicken a set A, we form C equals A complement and then form C complement. Depending on the nature of A, this procedure may result in some disconnected points. Therefore, thickening by this procedure usually requires a simple post-processing step to remove the disconnected points. We will notice in the next example that the thinned background forms a boundary for the thickening process. This feature does not occur in the direct implementation of thickening. This is one of the reasons for using background thinning to accomplish thickening. The figure shows set A, complement of A, result of thinning complement of A, thickened set obtained by complementing C, final result with no disconnected points. Skeleton. The notion of a skeleton S of A is intuitively defined. If Z is a point of S of A and D of Z is the largest disk centered in Z and contained in A, that is, one cannot find a larger disk that fulfills these terms, the disk is called maximum disk. The disk D of Z touches the boundary of A at 2 or more different places. The skeleton of A is defined by terms of erosions and openings, as can be seen in the following expressions, where B is a structuring element and A erosion B indicates K successive erosions of A. K times and K is the last iterative step before A erodes to an empty set. In other words, in conclusion, S of A can be obtained as the union of skeleton subsets Sk of A. The example for skeleton is shown on screen. A can also be reconstructed from subset Sk of A by using the equation where Sk of A dilation Kb denotes K successive dilations of Sk of A, that is, erosion and dilation. Fundamental operations. Morphological operations. Erosion, dilation. These operations are fundamental to morphological processing. Dilation. Dilation is used for expanding an element A by using structuring element B. Dilation of A by B is defined by the equation shown on screen. This equation is based on obtaining the reflection of B about its origin and shifting this reflection by Z. The dilation of A by B is a set of all displacement Z such that B cap and A overlap by at least one element. Based on this interpretation, the equation can be rewritten as shown on the screen. Figure shows set A, square structuring element, dilation of A by B, elongated structuring element, dilation of A using this element. Another example of dilation is shown on screen. Sample text of poor resolution with broken characteristics can now be seen. Dilation of B by A with broken segments joined. Erosion. Erosion is used for shrinking of element A by using element B. Erosion for sets A and B in Z squared is defined by the equation now shown. This equation indicates that the erosion of A by B is a set of all points Z such that B, translated by Z, is combined in A. On the screen we can see set A, square structuring element, erosion of A by B, elongated structuring element, erosion of set A using elongated element, duality between dilation and erosion. Dilation and erosion are duals of each other with respect to set complementation and reflection. That is, it can be represented as shown on the screen. One of the simplest uses of erosion is for eliminating irrelevant details in terms of size from a binary image. On the screen are seen image of square size, erosion, dilation. Fundamental operations of morphological processing. The hit or miss transformation, a basic morphological tool for shape detection. Let the origin of each shape be located at its center of gravity. If you want to find the location of a shape, say X, at a larger image, say A, let X be enclosed by a small window, say W. The local background of X with respect to W is defined as a set difference, W minus X. Applying erosion operator of A by X will get us a set of locations of the origin of X such that X is completely contained in A. It may be also viewed geometrically as a set of all locations of the origin of X at which X found a match or hit in A. Apply erosion operator on the complement of A by the local background set, W minus X. Notice that the set of locations for which X exactly fits inside A is the intersection of these two operators above. This intersection is precisely the location sought. If B denotes the set composed of X and its background, B equals B1, B2, B1 equals X, B2 equals W minus X. The match or set of matches of B in A can be represented by the equation and diagrams shown on screen. The reason for using these kind of structuring element, B equals B1, B2, is based on an assumed definition that two or more objects are distinct only if they are disjoint, disconnected sets. In some applications, we may be interested in detecting certain patterns, combinations of ones and zeros, and not for detecting individual objects. In this case, a background is not required. The hit or miss transform reduces to simple erosion. This simplified pattern detection scheme is used in some of the algorithms for identifying characters within a text. Introduction to Morphological Processing. Morphological processing. Morphology is a branch in biology that deals with the form and structure of animals and plants. Mathematical morphology as a tool for extracting image components that are useful in the representation and description of region, shape. The language of mathematical morphology is set theory. Unified and powerful approach to numerous image processing problems. In binary images, the set elements are members of the 2D integer space, where each element x, y is the coordinate of a black or white pixel in the image. Basic concepts in set theory. Subset, union, intersection, disjoint, mutually exclusive, complement, difference, reflection, translation. Logic operations involving binary pixels and images. The principal logic operations used in image processing are and, or, not, complement. These operations are functionally complete. Logic operations are performed on a pixel-by-pixel basis between corresponding pixels, bitwise. Other important logic operations: XOR, exclusive OR, NAND, not AND. Logic operations are just a private case for a binary set operation such as AND, intersection, OR, union, not, complement. Structuring element. Morphological processing is a collection of non-linear operations related to the shape or morphology of features in an image. Morphological operations rely only on the relative ordering of pixel values, not on their numerical values, and therefore are especially suited to the processing of binary images. Morphological operations can also be applied to grayscale images. Morphological techniques probe an image with a small shape or template called a structuring element. The structuring element is positioned at all possible locations in the image, and it is compared with the corresponding neighborhood of pixels. A morphological operation on a binary image creates a new binary image in which the pixel has a non-zero value only if the test is successful at that location in the input image. The structuring element is a small binary image, that is, a small matrix of pixels, each with a value of 0 or 1. The matrix dimensions specify the size of the structuring element. The pattern of ones and zeros specifies the shape of the structuring element. An origin of the structuring element is usually one of its pixels, although generally the origin can be outside the structuring element. Some examples of simple structuring elements. Square 3x3 element. A common practice is to have odd dimensions of the structuring matrix and the origin defined as the center of the matrix. Structuring elements play in morphological image processing the same role as convolution kernels in linear image filtering. When a structuring element is placed in a binary image, each of its pixels is associated with the corresponding pixel of the neighborhood under the structuring element. Fit all on pixels in the structuring element cover on pixels in the image. Hit any on pixel in the structuring element covers on pixel in the image. The structuring element is set to fit the image if for each of its pixels set to 1, the corresponding image pixel is also 1. Similarly, a structuring element is set to hit or intersect an image if at least for one of its pixels set to 1, the corresponding image pixel is also 1. Fitting and hitting a binary image with structuring elements S1 and S2. Zero-valued pixels of the structuring element are ignored, that is, indicate points where the corresponding image value is irrelevant. Morphological processing in grayscale images. 1. Dilation, grayscale images. Equation for grayscale dilation is shown on the screen. df and db are domains of f and b. The condition that s minus x, t minus y need to be in the domain of f and x, y in the domain of b is analogous to the condition in the binary definition of dilation, where the two sets need to overlap by at least one element. We will illustrate the previous equation in terms of 1 minus d, and we will receive an equation for one variable as shown. The requirements that the s minus x is in the domain of f and x is in the domain of b imply that f and b overlap by at least one element. Unlike the binary case, f, rather than the structuring element b, is shifted. Conceptually, f sliding by b is really not different than b sliding by f. The general effects of performing dilation on a grayscale image is twofold. If all the values of the structuring elements are positive, then the output image tends to be brighter than the input. Dark details either are reduced or eliminated, depending on how their values and shape relate to the structuring element used for dilation. The figure shows result of dilation of various positions of sliding B past F, complete result of dilation. Erosion, grayscale images. Grayscale erosion is defined as shown on screen. The condition that S plus X, T plus Y have to be in the domain of F and X, Y have to be in the domain of B is completely analogous to the condition in the binary definition of erosion, where the structuring element has to be completely combined by a set being eroded. The same as in erosion, we illustrate with 1D function. General effect of performing an erosion in grayscale images. If all elements of the structuring element are positive, the output image tends to be darker than the input image. The effect of bright details in the input image that are smaller in area than the structuring element is reduced, with the degree of reduction being determined by the grayscale values surrounded by the bright detail and by shape and amplitude values of the structuring element itself. Similar to binary image, grayscale erosion and dilation are duals with respect to function complementation and reflection. Opening and closing. Similar to the binary algorithms, opening can be represented by the equation as shown on screen and closing by this equation. In the opening of a grayscale image, we remove small light details while retaining relatively undisturbed overall gray levels and larger bright features. In the closing of a grayscale image, we remove small dark details while retaining relatively undisturbed overall gray levels and larger dark features. Some applications of grayscale morphology. Morphological smoothing. Perform opening followed by a closing. The net result of these two operations is to remove or attenuate both bright and dark artifacts or noise. Morphological smoothing images. Morphological gradient. Dilation and erosion are used to compute the morphological gradient of an image denoted by G, such as it is used to highlight sharp gray level transitions in the input image, obtained using symmetrical structuring elements, which tends to depend less on edge directionality. Top hat transformation. Denoted by H, it is defined as H equals F minus F opening of B. Cylindrical or parallel pipe structuring element function with a flat top. Useful for enhancing detail in the presence of shading. Textural segmentation. The objective is to find the boundary between different image regions based on their textural content. Close the input image by using successively large structuring elements. Then, single opening is performed, and finally a simple threshold that yields the boundary between the textural regions. Granulometry. Granulometry is a field that deals principally with determining the size distribution of particles in an image. Because the particles are lighter than the background, we can use a morphological approach to determine size distribution. To construct at the end a histogram of it, based on the idea that opening operations of particular size have the most effect on regions of the input image that contain particles of similar size. This type of processing is useful for describing regions with a predominant particle-like character. Opening and closing. Opening smooths contours, eliminates protrusions. Closing smooths sections of contours, fuses narrow breaks and long thin gulfs, eliminates small holes and fills gaps in contours. These operations are dual to each other. These operations can be applied a few times but has effect only once. Opening. First eroded A by B and then dilate the result by B. In other words, opening is the unification of all B objects entirely contained in A. The diagrammatic expressions of this can be seen on screen. Closing. First dilate A by B and then erode the result by B. In other words, closing is a group of points which the intersection of object B around them with object A is not empty. The diagrammatic representations of this can be seen on the screen. We can now see the use of opening and closing for morphological filtering. These contain the original image, erosion, opening of A, dilation of the opening, and closing of the opening.